All right, there's another way to do circuits when you have a a combination circuit. Specifically, when you've got one that's really complex with lots of little loops on it and that sort of thing going on. So you have like a battery over here, and you've got a loop and another loop, and this goes to another loop, and you got another resistor over here, and you've got a resistor hanging off this way, and then it comes back to here, and then you got another resistor. You're like, this thing gets ugly, and you're like, okay, this is the same as this. At some point, you realize, boy, this combination stuff doesn't work. Combination reasoning, it works, but it's just going to take forever. And so Kirchhoff came up with a way to solve problems using two things we already know about the circuits. One of which is that if I have a wire and it goes into two other wires, the current here has to be equal to the current here plus the current here. So in this case, we'd write something like I1 equals I2 plus I3. And that's always true because current is conserved. And so he would say you could write that down. And you wouldn't need to know much about a circuit to say that's true, right? So if I was looking at the circuit here, this is I1. This is I2, this is I3, and this is I4. So you could say I1 is equal to I2 plus I3 plus I4, and it's got to be true, right? There's no other options. Now your second thing that he ran into is this. He said, look, if I've got some sort of loop like this one right here, if I go around that loop and back to where I started, my potential difference, my voltage change has to be zero because I'm back where I started. So you would say something along the lines of, well, your voltage has to be zero, even though I went through this resistor here, IR, and had a voltage drop, and I went through this resistor here, let's say I drew I this way, minus, and it would also be I3, and have another voltage drop across this resistor here. Okay, these resistors would probably be different. And so this also has to be true. And from this, you end up with two equations and three unknowns. And we just need to do one or two more things like that. We can start solving for the current in these various resistors. And so Kirchhoff came up with that idea that two items there. One, current has to be conserved, so therefore I1 has to equal whatever it's going into. And the second one that he did is that that your potential difference has to be zero when you're done. So if you add up all the voltage drop, add in whatever batteries you might have, okay, you would end up with a way to solve problems using, multiple equations, multiple unknowns. Now, although this is handy for massively ugly circuits like the one I drew over here, it's even more handy for, well, it's not handy, it's essential for circuits that have, say, two batteries in it, something you did not deal with at all last year because it requires using Kirchhoff's law, and we weren't ready for that, right? And so now we got another resistor here, and I've got two batteries, and they're pushing against each other, and this suddenly makes a Kirchhoff's law situation. Although you could, in this particular case, sum up the batteries and do something clever like that. The truth of the matter is, this becomes a Kirchhoff's law problem because you have two batteries. Even more so, when you deal with capacitors and inductors, it starts to become much easier just to forget all this. This is like this, which is like this, and this is, just simply go, all right, I just find all my voltage drops as I walk around a loop. Okay, and it's got to work because my voltage difference has to be zero. But if I start at one place and end in the exact same place, right, then I have a loop's idea. Okay, so this was the introduction to Kirchhoff's law, and then we're going to switch. I'm going to do the example, okay, and then I'm going to give you a couple problems to do. All right, so here we are at that point, so I'm going to go ahead and end this video, and we'll start on the next one, the example problem. Go ahead and look at the example problem, see how awful it is, see how you would have to put the combination together. By the way, you could do that circuit using the combination ideas we had before, but I'm hopefully going to convince you that at this point is about the threshold when you start using Kirchhoff's law and go, oh, that is better, or at least it's you're less likely to make a kind of a silly mistake that hurts you.